So I want to continue our discussion of functional group transformations today as we begin to move through synthetic organic chemistry over the next few weeks. And what I wanted to do, I've sort of tried to break up the chapter. The chapter is sort of a staccato collection of different reactions, many of them review, some of them new. And you'll get to reinforce them in the problem set. I've picked, I think, 17 sort of nice problems that pick up concepts from the chapters and review functional group transformations. But I've tried to break up our discussion of the chapter into some at least loose themes. And the first theme I thought was oxidation state as a way of thinking about functional groups. Today what I want to do is talk about oxidation and reduction reactions and maybe have a chance to touch on some aspects of stereoselectivity that I think are cool and significant. Also, again, to maybe talk about themes. So, okay, if you're talking about oxidation, let's start with oxidation. And if you're talking about oxidation of alcohols, then we're talking about going to aldehydes and ketones, depending on the flavor of alcohol, primary or secondary, and carboxylic acids, depending on the exact conditions. And I wanted to set the oxidation reaction. There's many oxidizing agents to oxidize alcohols on up to aldehydes, ketones, and carboxylic acids. And I wanted to set a little bit of a theme and then show both some traditional oxidizing agents and some newer ones, but really set them into the context of a theme of how and why they work. So if I take some generic alcohol, an alcohol that has an alpha hydrogen, obviously you can't oxidize a tertiary alcohol to a carbonyl compound without breaking a carbon-carbon bond. But if you have a primary alcohol or a secondary alcohol, it can be oxidized to an aldehyde or a ketone. And the basic theme that occurs is with some oxidizing agent, you form a bond between the oxygen of the alcohol and something that is going to become a leaving group. Your oxidizing agent is going to get reduced in the process. And this is basically your oxidizing agent. And then what happens is an elimination reaction, like so. So I'll write elimination just to maybe drive the point home. And the overall result now is that we get our carbonyl and we get a leaving group leaving off of the oxygen. So if I want to begin with an oxidation reaction, sort of an old classic, I would probably talk about Jones oxidation. One of the most common and traditional oxidizing agents is high-valent chromium, typically chromium-6. Chromium-6 is a powerful oxidizing agent, also readily available in the form of chromates and dichromates. And so a Jones oxidation involves taking an aldehyde or a ketone, I'll just draw it as R and R prime, treating it with, usually it's chromic acid, at least you'll often see it written as HCr2O4 in sulfuric acid, usually with an organic co-solvent that's not oxidized like acetone. Typically what this means, you wouldn't usually be able to buy a bottle of chromic acid, but if you take potassium chromate and you throw it in sulfuric acid, you generate chromic acid in situ. Or if you take potassium dichromate and throw it into sulfuric acid, you generate chromic acid in situ. So chromic acid has the structure like so. Chromic acid is, as I said, a chromium-6 species. And if you take chromic acid or potassium chromate or potassium dichromate or chromium trioxide, which is the anhydride of chromic acid, throw it in with sulfuric acid and acetone, you will get out the carbonyl compound. And what I wanted to do in this example here, really, this is one I presume you've seen in sophomore chemistry, right? Who's seen this in sophomore chemistry? Okay. What I wanted to do with this example really was to go ahead and talk about the mechanism of this reaction in terms of common themes. So here's your alcohol. And even though chromic acid is an inorganic acid, you've seen the theme of a carbonyl and an OH combining with an alcohol, right? That's an ester formation. And all you're doing here is forming an inorganic ester, a chromate ester, just like you would form an organic ester under acidic conditions. And at this point, you're set up for your elimination reaction. And all you need to do is think about, okay, now we're going to form the bond, double bond to an oxygen, lose a proton. Of course, you could have a base, wouldn't be hydroxide, but it might be water helping to remove the proton. You can push electrons onto the chromium, push electrons up onto the oxygen. And here we go. Here's our carbonyl compound. And of course, as I said, you've lost a proton. But where I wanted to go with this was just to point out that now in pushing our arrows, now we've gone from chromium-6 to chromium-4. And remember, in the previous lecture, I was talking about themes of oxidation, that oxidation states move in twos. When we oxidize an alcohol to a ketone or an aldehyde, we move up 2 oxidation state units on the carbon that's being oxidized. We've moved up 2 oxidation state units here. It makes sense then that now you've moved from chromium-6 to chromium-4. Chromium-4 isn't stable. Chromium has stable oxidation states of 2, 3, and 6. As I said, chromium-6 is a good oxidizing agent. Chromium-3 is a good stable oxidation state. So ultimately what happens is you get disproportionation reactions where your chromium-4 disproportionates to chromium-5, which goes down to chromium-3, and the chromium-5 goes down to chromium-3 in another oxidation reaction. In other words, if I were to write a balanced equation, remember I talked before about oxidation states, and I wanted to write a balanced equation of stoichiometry, I'd say, okay, our carbon is going up by oxidation state of 2. Ultimately, our chromium is going down by oxidation state of 3 from 6 to 3. I would expect to be able to use 3 moles of alcohol per mole for 2 moles of chromium to have complete reaction if I'm oxidizing, say, a secondary alcohol up to a ketone. Thoughts or questions at this point? Because this really sets the theme for what we're going to be talking about. So Jones reagent is a good workhorse reagent. These days it has largely fallen out of fashion because chromium-6 is toxic and carcinogenic. And while use in the laboratory isn't a big deal on a small scale, you generate toxic waste that's harder to dispose of, and on a larger scale, it becomes problematic. Also, because chromium-6 is carcinogenic, people try not to work with it. The real issues with chromium-6 haven't been so much small-scale laboratory use, but it's widely used in electroplating, meaning making chrome-plated steel and the like, automobile parts and other parts where you have vast vats of chromium. And then the waste stream from that can lead to contamination of the water supply and even cancer, as was outlined in the movie Silkwood. All right, but coming back to the laboratory, one of the limitations of Jones reagent is you can't really control it. In other words, if I start with a primary alcohol, I can't stop at the aldehyde. I end up going all the way up to the carboxylic acid. So I'll write can't stop at aldehyde. The problem is that the aldehyde under aqueous acidic conditions forms the hydrate. So I'll write with aldehyde plus H2O is in equilibrium with the hydrate, the geminal diol. Geminal diols in general, with the exception of a few compounds, aren't stable compounds that you can put in a bottle. They're in dynamic equilibrium with the aldehyde. If I try to distill or isolate the geminal diol, I lose water. It goes back to the aldehyde. But nevertheless, it forms transiently as the geminal diol. And now you have the exact same scenario where you have a hydrogen alpha to a carboxylic acid. And so the geminal diol goes up to the carboxylic acid. So as a result of this, and because there's a desire in synthetic organic chemistry, indeed a compelling need to have control, to be able to choose the outcome, to get a carboxylic acid if you want it, but not if you don't want it, organic chemists have developed reagents, tools, to control the outcome of reactions. And so notably, an early example was the development of reagents that would allow one to stop at the aldehyde. For example, again in the theme of chromium-6, PCC, pyridinium chlorochromate, under non-aqueous conditions allow oxidation to the aldehyde with control. And just let me draw the structure of PCC. So the theme is very similar, except we're doing this without any water present. You still have chromium-6. It's a chromium derivative called the chlorochromate ion, or the pyridinium salt thereof. So the mechanism really is pretty similar in that you form an ester, but now you form a chromate ester, but now you don't have water to go ahead and carry out further formation of the geminal diol and subsequent oxidation to the aldehyde. Other reagents have been developed. Chromium trioxide is another chromium-6 reagent. Chromium trioxide, let me write that a little more neatly, CrO3.2-pyridine, basically pyridine coordinating to the chromium, is sometimes referred to as Collins reagent. And provides another alternative to PCC It's less acidic, which in some cases can be very helpful in the sense that acid can carry out other reactions. I'll show you an example later where we had a desperate need for control of very mild conditions in an oxidation reaction. So right now it's just one of the multitude of oxidizing agents that have been developed. So as I said, chromium has gotten itself a bad rep as a toxic and hazardous material, and many other oxidation reactions have been developed. One of the most popular ones is the Swern oxidation. The Swern oxidation uses sulfur as the oxidizing agent, ultimately, dimethyl sulfoxide, but involves a number of other reagents. So again, if we take an alcohol, and I'm going to show you deliberately a primary alcohol, because I want to show you you can stop at the aldehyde, and we treat that alcohol with oxalochloride. I'm going to write it, I'll write it the way you will often see it written, but it's very non-intuitive written this way. I'll write it as COCl bracket twice, and I'll draw out the structure in just a moment, and triethylamine, and then you add, and dimethyl sulfoxide, and then you add triethylamine. The overall reaction gives rise to oxidation to the aldehyde, or if we used a secondary alcohol, it would give rise to the ketone. So the basic gist of the mechanism is that dimethyl sulfoxide, and I'm going to write it showing its dipolar nature. Dimethyl sulfoxide is nucleophilic and basic on oxygen. Here's your structure of oxalochloride. Oxalochloride is the double acid chloride of oxalic acid. So it's an acid chloride next to an acid chloride. Acid chlorides are very electrophilic. Having two acid chloride groups right next to each other, you have delta positives, partial positive charges on both carbons. Those carbons are super electrophilic. So you have a nucleophile, you have your dimethyl sulfoxide, and it attacks the carbonyl. You kick electrons up onto the oxygen, form a tetrahedral intermediate, kick electrons down, kick out chloride. I won't go ahead and show you all of the steps. You should be able to write them. But in 2 steps, now we go ahead, we kick out chloride. Now at this point, so I'll just write arrow, arrow, just to remind you at 2 steps. At this point, chloride can come back, attack the sulfur, and I love oxalochloride mechanisms because they're one of the few mechanisms in which a carbon-carbon bond gets ruptured. The central carbon-carbon bond of oxalochloride in a number of different reactions, including its use to form acid chlorides, where it's a useful reagent to transform carboxylic acids to acid chlorides, the central carbon-carbon bond can break. The overall result here is that you get a chlorodimethyl sulfonium ion plus carbon dioxide plus carbon monoxide plus chloride. In effect, what you've done is take the oxygen on dimethyl sulfoxide and replace it with something that's a leaving group and make that sulfur good and electrophilic. At that point, we're all set up to get into the manifold of reactivity that we've been seeing with all of this theme of oxidation. So here's our alcohol. Here's our chlorodimethyl ion. Here's our base, triethylamine. As you can imagine, the base can pull off the proton can attack, the oxygen can attack the sulfur. I won't go through the details of that. You can write that mechanism in a couple of different ways depending on whether you want to think about the alcohol attacking the sulfur first and then losing a proton or vice versa. But the overall result now is just as in the case of the chromium oxidations, just as in the case of our generic reaction where I put an X initially there, we have now set up for having an elimination occur where now we can have our triethylamine base pull off the proton, kick in, do an elimination here to give our aldehyde plus dimethyl sulfide plus a triethylammonium ion. And you notice in this overall process, sulfur has changed oxidation state. We've gone to dimethyl sulfide where our sulfur is in the -2 oxidation state. We started with dimethyl sulfoxide where our sulfur was in the 0 oxidation state. Thoughts or comments? There are a few flavors of the Swern oxidation with slightly different variants of how one gets to that chlorosulfonium ion that you might see. But the Swern oxidation is probably my go-to workhorse oxidation reaction because it uses cheap, readily available reagents and doesn't generate any major toxic byproducts. Obviously, many chemicals have toxicity, but you don't have the same issues with the chromium. Another popular reagent, so basically you have the whole periodic table here at your disposal for oxidation. You've got the transition metals like chromium-6, manganese. 7 is another good oxidizing agent. In osmolation reactions, you have osmium-8. I'll show you rhenium-6. You've got the whole center of the transition state of the periodic table with the transition metals. You've got the right-hand side of the periodic table, and while you don't have that much variation in oxidation state in the case of oxygen and nitrogen and carbon and so forth, although you can traipse around with, say, hydrogen peroxide, as you move down, you get more oxidation states. Iodine is one of my favorite elements because it just occupies this wide range of oxidation states all the way from -1 to +7 quite happily. And in the case here that I'm going to show you of a Des-Martin oxidation, the Des-Martin periodinane is another very useful oxidation. So the Des-Martin reagent is an iodine 5 reagent, what's often referred to as a hypervalent iodine. Again, as one moves down the periodic table and invokes the d orbitals, you can have hexacoordinate and even higher coordinate forms of the elements. So this particular iodine reagent, this particular hypervalent iodine reagent, has 5 groups around the iodine, 3 acetoxy groups, plus a carboxy group and an aromatic ring. And this particular reagent and a few variations on it are nice oxidizing agents for alcohols and follow the same theme. So if we have our primary alcohol, I'm showing you primary alcohols here because it's nice to be able to stop at the aldehyde and it differentiates. But of course, we could use it for a secondary alcohol to go to the ketone. So basically, you can think of the iodine, and indeed in many of these reactions, as we saw in the chromate reaction, as we saw with the chlorosulfonium ion, you can think of the iodine as being very prone to having nucleophilic attack by another oxygen. That's what we had with chromium, with chromic acid. That's what we had with the chlorosulfonium ion. And so keeping up with this theme, if we lose acetic acid, we can displace acetic acid. You could think of it as SN2 or addition elimination. I would think of it as addition elimination. But however you want to dice and slice it, what you get at this point is this same type of theme now, where you've got a leaving group on the oxygen and you're able to break the bond. And so if you go ahead and you break the bond, form a carbonyl, go ahead, kick electrons onto oxygen, kick out acetate, so you go minus H plus, minus ACO minus, then your overall result is to get you to the aldehyde. And the iodine has dropped in oxidation state again by 2 from iodine 5 to iodine 3. Yeah. Oh, thank you. Yes. The aldehyde, thank you. So my own experience, I'll just give you sort of firsthand. We were looking at the oxidation of a sensitive alcohol, and we were trying to oxidize this alcohol to the corresponding aldehyde for a Diels-Alder reaction. And when we tried this reaction, first we tried it with a Swern oxidation. And aldehydes, so we tried it with a Swern oxidation, and the double bond moved into conjugation. Basically, you get the aldehyde at this position, and at this point, the CH2 group is very acidic because it's next to an aldehyde, which brings its pKa down to maybe a little below, somewhere around 20, and a double bond conjugation brings it down further. And so we found that we were losing this proton. But with Des-Martin oxidation, that saved the day for us and allowed us to go ahead and carry out the oxidation reaction. I guess I want to reflect on one theme of modern synthetic organic chemistry. And I think the theme of modern synthetic organic chemistry is to be able to do things, carry out reactions cheaply and efficiently. DMSO is pretty cheap. Oxalic acid, oxalic chloride, not quite so much. Des-Martin periodinane is not so cheap. But if you go catalytic and use a really cheap oxidizing agent, then you can carry out reactions very efficiently. And so I want to show you one other modern example, TPAP oxidation. This is a catalytic. TPAP stands for tetrapropyl ammonium perruthenate. And if you look in the periodic table, you'll see that ruthenium is over on the right-hand side of the on the left-hand side of the transition elements just below iron, and can assume a variety of oxidation states. So we have +7 ruthenium. Here's your reagent, PR4N plus RuO4 minus. Kind of reminds me of permanganate, even though it's not directly under manganese. And we use it as a catalytic oxidant. And then we use a cheap material, N-methylmorpholine N-oxide, NMO, as our stoichiometric oxidant. You've seen morpholine when we talked about heterocycles. N-methylmorpholine is morpholine, the 6-membered ring with an oxygen and a nitrogen and a methyl group. And N-methylmorpholine N-oxide is the oxide, the amine oxide. And so you can get a catalytic cycle if you go ahead and use conditions and oxidize using just a catalytic amount of the ruthenium. So if you take a primary alcohol, and again you have control, you run the reaction under anhydrous conditions. And so if we take catalytic TPAP and stoichiometric NMO and carry out the reaction in the presence of molecular sieves. Molecular sieves soak up any water. Usually we carry out this reaction in methylene chloride. We can oxidize a primary alcohol to an aldehyde or a secondary alcohol under the same conditions. I'll just write ditto to a ketone. Thoughts or questions? Sometimes said if there's a dozen ways to do a reaction, there's no one good way to do a reaction. Oxidation reactions, in a way, you could say in a synthesis, count as, you could call it overhead, in the sense that a synthesis typically involves building up a complex molecule from a simpler molecule. Changing oxidation state is just something annoying that you have to do along the way. And so many reagents have been developed as tools to facilitate oxidation. Bleach, oxygen, or other ultimate oxidizing agents, hydrogen peroxide, that get used under a variety of conditions. When we move into chapter 7, we'll start to focus on carbon-carbon bond forming reactions, and you'll get to see themes of forming an alcohol, having to oxidize it up to a carbonyl, forming another carbon-carbon bond. All right, so I want to sort of flip the tables here, since I've tried to theme things oxidation and reduction, and say, all right, if you have an alcohol and we carry out oxidation, as I said, we go to an aldehyde or a ketone, or all the way up to a carboxylic acid. And then conversely, if we have an aldehyde or ketone and we carry out a reduction reaction, we reduce it down to an alcohol. And I want to take a few minutes to talk about reductions. We looked last time at lithium aluminum hydride and sodium borohydride, right? So if I take acetophenone and I treat it with sodium borohydride and ethanol or methanol, some alcohol solvent, I can reduce it to the corresponding alcohol. Ditto, if I go sodium borohydride, NaBH4 is sort of a moderate reducing agent. Lithium aluminum hydride is a sledgehammer. If I take LiAlH4 and THF or ether, and then carry out an aqueous workup with H3O plus, or in some cases with base, again, I can go to the corresponding alcohol. What I want to do at this point, I think, is talk a little bit about some aspects of the chemistry that are a little subtler and maybe go beyond the sophomore level for these reduction reactions. And I want to show you some issues of stereoselectivity and get us thinking about those. In most cases, synthetic organic chemistry is about control. It's about getting one product that you want to the exclusion of the others. Oxidation of a primary alcohol to an aldehyde to the exclusion of the carboxylic acid is one example of control. Being able to oxidize a primary alcohol in the presence of a secondary alcohol is another aspect of control. These are chemoselective controls. What I want to talk to you about is stereoselectivity, and I want to talk about steric and stereoelectronic influences, and I'll just show you a few studies and get us thinking about steric and stereoelectronic factors. All right, if we have sodium borohydride and we have this bicyclic ketone, so we've seen before bicyclo 2,2,1 heptane systems. This is bicycloheptane 2,2,1 one. It's the ketone. You can add either hydride from the bottom face or hydride from the top face. If you add hydride from the top face, if hydride comes in from the face of the smaller one-carbon bridge in this bicyclic system, then you end up with the product in which the OH points down and the hydrogen points up. Conversely, if hydride adds from the bottom face, you end up with the stereoisomer, you end up with the diastereomer, in which the OH points up and the hydride that's added points down. Which face do you think is preferable? Which one do you think? The first one. Why?
Because that's the end of stereochemistry, which is overlapping with the orbitals on the other side.
Overlapping with the...
Like the orbitals of the oxygen are overlapping with the orbitals of the adjacent carbon, which is what gives it that stabilization.
And that may be part of it, and part of it may be, so part of it may be the stereoelectronic overlap. Part of it is probably a plain steric fact that the endo face here is more blocked, right? You've got a concave endo face here and a convex exoface. And so the preference isn't huge, but it's substantial. You get 86% and you get 14%. Now, what's interesting is if we take the same compound, Now, and we simply add 2 methyl groups on the 1 carbon bridge. So if you take the same compound, you add 2 methyl groups on the 1 carbon bridge, carry out the same reaction, the same reduction, so I'll just say NABH4 here, and now we're dealing with the same type of competition, but with the 2 methyl groups. What do you think happens to our stereoselectivity now? It becomes substantial. So you think that now we get endohydroxy or endohydroxy or endohydrogen? Which do you think is the major product for starters? Endohydroxy. How many people think endohydroxy now becomes the major, very major product? How many people think exohydroxy? Right, why do you think exo?
I would think the 2 methyls on the 1 carbon bridge create like way more steric hindrance, so it's harder for that sodium borohydride to get in there.
And the winner ends up being, winner ends up now being the OH on the exo face. In fact, the stereoselectivity happens to flip from 86 to 14 to 14 to 86. Basically, your hydride now has to come in from this face, and it's banging against the methyl group here. So basically, you've got these competing interactions involving primarily sterics. And you can really window these interactions by windowing the size of your borohydride reagent. So one of the ways people often like to probe stereoselectivity is they'll go ahead, they'll take, say, a 6-membered ring and conformationally lock it. So a 6-membered ring with a tert-butyl group, a cyclohexane with a tert-butyl group, is basically locked, having the tert-butyl group in the equatorial position. If they take a borohydride reagent and carry out a reduction, 2 products are possible. You get the axial product, in other words, the diastereomer in which the OH group is cis to the tert-butyl group, or the cis diastereomer, and you get the equatorial product, the product in which the OH group, the hydroxy group, is trans to the tert-butyl group. And if you take sodium borohydride and carry out this reaction, you get 20 to 80 stereoselectivity. And you can imagine that you've got factors going both ways here. So here's our Here's our carbonyl compound. And in order, I should draw in my hydrogen over here. And in order for the borohydride reagent I'll just write this as Br3-. In order for the borohydride reagent to go ahead and form the equatorial product, you have to go ahead and add in from the top face, and you've got these axial hydrogens here getting in the way. So you can say, all right, on the downside, we've got the potential for sterics here. In other words, this is going to give rise to and it's not so bad in this case with sodium borohydride. In other words, 4 out of 5 times borohydride adds from the axial position. As I said, organic chemistry really is, synthetic organic chemistry really is about control. And if there's one diastereomer possible, synthetic organic chemists want to be able to get the other diastereomer as well, to have the synthetic methodology to choose one way or another. And graduate students and postdoctoral students and undergraduate students doing research in synthetic organic chemistry and synthetic methodology often develop reagents to provide control. So a way of favoring avoiding the steric or avoiding this product and maximizing, so avoiding the equatorial product, and maximizing the axial product is to go ahead and come up with a bulky reagent. And one of the reagents that's been developed is lithium trisec-butyl borohydride. So you have 3 sec-butyl groups on your boron, like so. This reagent is sometimes called L-selectride. It's always fun if you invent a compound to be able to, or a reagent, to name it. L-selectride is stereoselective, and it flips the stereoselectivity and brings us to 97-3. Basically, now you make these steric interactions so disfavorable that you go ahead and force it to add from the other face. Now, if you can get a little bit of reasonable amount of stereoselectivity, then the question becomes, okay, how can you mentioned 99-1, how can you get even greater? And the idea becomes add more steric hindrance, and it turns out that going from a sec-butyl group to an isoamyl, or sometimes called siamyl group, adding a methyl group takes us, whoops, I need my boron here. This reagent takes us all the way to 99-1, or greater than 99-1 selectivity here. This reagent gets called LS selectride. Now, I've pulled a little bit of a fast one on you because I've told you what's bad about addition from the top face, but I haven't told you anything that's bad about addition from the bottom face. Now, you brought up the idea of orbital interactions, and this is indeed the issue, that as you're adding, you're starting to form a bond over here. You're starting to break a bond to boron. You're starting to form a bond over here, a single bond to oxygen. I'll draw this sort of splayed here as we're moving toward the tetrahedral state. Now, what's happening at this point with these hydrogens here is you are getting eclipsing interactions. And eclipsing is bad for a stereoelectronic reason. If you think back to sophomore organic chemistry and you think to rotation about ethane, we all remember that eclipsed ethane is bad. It's greater than it's 3 kilocalories per mole above staggered. Right, 3 kilocalories per mole above the staggered conformation. And hopefully we remember that what's bad about it is not what you might think of the hydrogens banging into each other, not a steric effect, but rather, because the hydrogens aren't that big, but rather it is orbital overlap. I'll say overlap of filled orbitals that occurs in the eclipse state. And this is exactly the same as what's occurring here as you're moving into the transition state, as your hydride is coming in at what's called the Burgi-Dunitz trajectory. And so eclipsing is a stereoelectronic phenomenon, meaning phenomenon involving orbitals. And so basically, we are again set with competing reactions. If our borohydride isn't too bulky, then we prefer to get addition from the top face because the bottom face is disfavored for stereoelectronic reasons. On the other hand, if your borohydride is very bulky, as in selectride, L-selectride, or LS-selectride, then steric factors dominate, and you go for what is a slightly less stereoelectronically favorable transition state. All right, we will pick up maybe talking about a little bit of acyclic stereochemistry next time and some mechanisms.